Okay, hints for homework 2. Problem 1. Prove that if b and c are relatively prime, then for any integer a, if I want to calculate the greatest common factor of a and b times c, we just find the greatest common factor in a and b and multiply by the greatest common factor of a and c. And intuitively this makes sense because b and c have different sets of prime factors. So how do we write down a formal proof? Well, one of the key tricks on using the fundamental theorem of arithmetic, which is every number has a unique factorization, is that we can use the same set of primes for a, b, and c. Okay, so let's say a is the product of I going from 1 to k, pi to the ei, for some distinct primes pi, and non-negative integers ei. Okay, so this is going to be the prime power factorization of the number a, and I'm going to use the same prime powers for b and c. But the powers are going to be different, the same primes I'm going to be using. So pi to the fi, let's say, for some fi greater than 0, and c is pi to the gi. Well, I guess we should just say we've already introduced the pi's in the first one, so this is just for some fi greater than or equal to 0, for some gi greater than or equal to 0. So why is it that I can use the same prime, since obviously a, b, and c don't have the same prime factors? In fact, b and c are relatively prime. Well, we can do that because I'm allowing the exponents to be 0. So it's just a convenient trick for writing proofs to throw in zeros for primes that really don't occur in the factorization. Okay, then what does bc equaling 1 mean in terms of the prime powers? Well, that means that a given prime pi cannot occur in both b and c, so one of these two exponents has to be 0. So this would mean that ei is 0 or fi is 0 for all values of I. Okay, and then think about what our formula is for the greatest common factor of two numbers. And let me just give you an example. So the GCD of a and b, we've seen, is the product, I goes from 1 to k, of pi to what power? Well, it has to be a factor of both a and b. So the biggest power of pi we can have would be the smaller of the two exponents ei and fi. So you take the minimum of these two. And do the same thing for AC and for ABC, and then show that we have this equality. All right, so just play with it like that. On to problem 2. Prove that for any positive integer n, we can uniquely express it in the form n is a times b squared, where a and b are natural numbers, and a is square free. Okay, and again, you are free to use the fundamental theorem of arithmetic. So I would just start by saying let's let n be product I equals 1 to k of pi to the ei power. And I want to find some perfect square. So some of the ei's are going to be even numbers, and some are going to be odd numbers. That's the way you want to think of it. So break it into maybe two different collections. Say L. So you can reorder them. And these are ei is even. And then maybe product I equaling L plus 1 to k. And these are going to be the odd powers. Okay, so all of these exponents have a 2 in them, and all of these are of the form 2k plus 1. And, well, I'll let you just introduce it. So here you could say maybe the ei is 2 fi, and these ei's would be of the form 2 fi plus 1 for some fi's, some natural numbers, fi's. These fi's could, of course, be 0. Maybe it just occurs to the first power. And then just kind of regroup things to get it expressed in this form, ab squared. And then use the uniqueness in FTA to show that this is really a unique type of decomposition. Part B. Suppose n is ab squared with a square free, and let d be some natural number. Prove that d squared is a divisor of n if and only if d is a divisor of b. Okay, so we'll just go ahead and use some new notation for a, b, and d. So again, use the same set of primes. I'll let a be the product I equals 1 to k of pi to the ei. Now a is square free, so that would mean the ei's are zeros or 1. B can be any integer. So say pi to the fi. And let's let d product. So notice I'm using the same set of primes where I'm allowing the exponents to be 0 if necessary. Pi to the gi. Okay, so n would be what? It's going to be a product of pi to some power, and d squared is going to be the product of pi to some different power, and d squared divides n. D squared divides n. Okay, so if you have two prime power factorizations, what does it mean to say one number is a factor of another number? Well, that would mean that this exponent here should have what relationship with this exponent here? Okay, so take it away like that. Homework 2, problem 3. Prove that if n is a positive integer having no prime factor less than or equal to the square root of n, then n is in fact a prime. Okay, this is a classical proof by contradiction. And that may be enough of a hint if you want to get started. Proof by contradiction. So what does that mean? You're going to use the same hypotheses, but you're going to assume the opposite of what you're trying to conclude. So we want to assume that n is a composite. So suppose, again, the hypotheses, n is a positive integer having no prime factor, has no prime factor p less than or equal to the square root of n, and that n is composite. So we're assuming the opposite conclusion. And let's see what goes wrong. Okay, so what does composite mean? Well, then n has a factorization that's non-trivial. So non-trivial means one of these or both of these factors are strictly bigger than 1. Some natural numbers, and they're strictly less than n. Okay, then n is of this form. Well, what can you tell me about the size of one of these numbers? So let's go ahead and assume that a is the smaller one. Less than or equal to b. What can you tell me about the size of a? So I want you to show a is at most square root of n in size. Okay, and then knowing that a is at most the square root of n, what can you tell me about every prime factor of a? So let p be a prime factor of a. Now, why do you know that a will have a prime factor? Think about that for a second. So why does it exist? And then what can you tell me about the size of that prime? And what can you tell me about the divisibility of n and that prime p? So I'll let you take it from there to obtain some contradiction. Problem 4. Show that z square bracket minus square root of negative 6 is an example of an integral domain in which irreducibles are not always primes. So this set, it's kind of like the Gaussian integers, except here we're just forming all objects of the form a plus b square root of negative 6, or you can think of that as a plus b square root of 6i, where a and b can be arbitrary integers. That is an integral domain. It's a subset of the complex numbers closed under addition and multiplication, etc., etc. Okay, part 1. Let's show that 2 is irreducible. So irreducible means 2 can't be expressed as a product of two objects that are non-units. And I'll do this by introducing the delta function. It's like the delta function we had for the Gaussian integers. Just take the square of the absolute value of a plus b root negative 6. So again, where does this absolute value come from? You're thinking of this as being a complex number, and so the absolute value is just a squared plus 6 times b squared. And again, this absolute value is a multiplicative property, multiplicative function. So delta of wz is delta w times delta of z for any two complex numbers in this integral domain. Okay, so I want to show 2 is irreducible. So we start by saying, suppose 2 breaks up as a product say u times v, for some u and v in this domain. Take the delta function of both sides, use the multiplicative property, and we get delta of u is times delta of v is delta of 2. Okay, well, what is delta of 2? Delta of 2 is 2 plus 0 times the square root of negative 6, so its delta value is 2 squared. Okay, so how is it possible? This is a natural number, and this is a natural number. Think about how is it possible for the product of two natural numbers to equal 4? And then you have to realize that this natural number delta of u is of the form a squared plus 6b squared. So think, can we have delta of u equaling 2? And then if delta of u is 1, what does that tell you about the object? So we're trying to conclude, what's the goal? We're trying to conclude that either u or v must be a unit. That would tell us that 2 is irreducible. If the only way to break it up requires that one of these two objects be a unit. Okay, so you play with it like that. And then the second part, well, okay, no, this is the hint here. Okay. So I'm getting ahead of the game. Suppose 2 is this. It applies delta. All right. So I'm just redoing the hint I already stated in the problem. Problem 4, continued. Show that 2 is not a prime by showing that 2 is a factor of this product, but not a factor of either one of these two pieces. So remember, the definition of a prime is that if P divides uv, then P divides u, or P divides v. So if that property fails, then P is not a prime. And so we're going to show that the number 2 fails to have that defining property. Okay, so why is this true? That one you can just multiply out the right-hand side and it should be very straightforward. Okay, so you just go ahead and multiply these two and show that 2 is a factor. Now remember, what does it mean to say 2 is a factor? This means you're working in the domain z bracket square root of negative 6. So you need to show that 2 times some object of this form equals the right-hand side. Okay, so this is what 2 dividing something means. 2 dividing the right-hand side would mean this. And, okay, and again for this part, it's the same thing. What would it mean to say 2 is a factor of 2 plus this, say? Well, that would mean that 2 times some a plus b square root of 6 should equal 2 plus square root of negative 6. And show that that's impossible. Problem 5. Okay, the next two problems will characterize all of the primes in the Gaussian integers. So let's recall the Gaussian integers is a Euclidean domain because it has the Euclidean algorithm that was on your last homework problem, and therefore it's a unique factorization domain. So prime and irreducible mean the same thing, unlike the previous problem. So suppose that p is a prime in the integers that can be expressed as a sum of two squares. So p is a squared plus b squared for some natural numbers a and b. For example, 5 or 13. They can each be expressed as a sum of two squares. Let's let pi represent the number a plus bi. I want to show that pi and its complex conjugate are irreducible. And thus, when we take p, we can break it up into this prime factorization right here. And the hint here is to say, use the multiplicative function delta to do this. So what is our task? Show that pi and the conjugate are irreducible. Okay, so let's just focus on pi. Let's show pi is irreducible. And our assumption is p is a sum of two squares. So I'm given p is a squared plus b squared, and pi is a plus bi. Well, let's try to factor pi. So let's say pi equals u times v for some elements u and v in this integral domain, Gaussian integers. Apply delta to both sides. Use the multiplicative property of delta. Okay, what's delta of pi? Well, delta is a squared plus b squared. That equals p. All right, so we've got p is delta of u times delta of v. Now p is a prime in the integers. This is a natural number. This is also a natural number. So everything going on is in the natural numbers. So I have a prime is a product of two natural numbers. Well, what does that tell you? And think about, what is my goal here? My goal is to show pi is irreducible. So once again, we want to prove that either u or v must be a unit in the Gaussian integers. And what are the units in the Gaussian integers? Yep. Units plus or minus 1 and plus or minus I. Those are the units in the Gaussian integers. Okay. And then this second part right here is a trivial thing. So go ahead and verify that. Continuation. Okay, problem 6. Suppose that p is a prime in the integers that cannot be expressed as a sum of two squares. Show that p is a prime in the Gaussian integers. Show that p is a prime in the Gaussian integers. Okay, now remember the Gaussian integers are a unique factorization domain, and so prime and irreducible mean the same thing. So I want to show that p, this integer prime, is irreducible in the Gaussian integers, that you can't break it up as a product of two Gaussian integers in a non-trivial way. So let's try to break up p. So suppose p equals u times v. for some Gaussian integers u and v. Okay, we've seen this a couple times now. If I want to prove that p is a prime, I want to prove that either u or v is a unit. And how do we do that? We use the delta function. Use the multiplicative property. And we get delta of p is delta u times delta v. The delta function applied to p is what? P squared. Okay. And again, this is all natural numbers. This is a natural number. This is a natural number. How is it possible to have a product of two natural numbers equaling p squared? Well, there's only a couple ways that can happen. You could have blah, 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 1 times p squared, or you could have p times p. But at some point here, you're going to bring back this hypothesis. P is a prime that cannot be expressed as a sum of two squares. Okay, so consider these possibilities for how do you break this up and then use this property to show that either u or v is a unit. And that will tell us that p is irreducible. Okay, then explain why every prime in the Gaussian integers is a divisor of some prime in the integers, and therefore must either be a prime in z that cannot be expressed as a sum of two squares, or a prime of the form a plus bi, where this is the decomposition of p as a sum of two squares. Okay, so let's focus on this first statement. Explain why every prime in the Gaussian integers is a divisor of some integer prime. So let's let say u be a prime in the Gaussian integers. Okay. Then u is a factor of u times its conjugate, or it's a factor of the delta value, whatever you like to say. Right? It's a divisor of that in zi. But this is a natural number. So let's say u conjugate has some prime power factorization in the natural numbers. Right? That's a natural number. So it has some prime power factorization in the natural numbers. U is an irreducible element. It's a prime in the Gaussian integers. So u is a divisor of this product. Well, if it's a divisor of that product, what does that tell you about its relationship to one of these primes in here? So I wanted to prove that u was a divisor of some prime in z. Okay, so I think you're at that point. And therefore, it must either be a prime in z that cannot be expressed as a sum of two squares. Okay, so now we just use the previous couple parts that tell us exactly how primes in the Gaussian integers, how primes in the integers factor in the Gaussian integers. Problem 7. Prove that for any positive integer m, if a is congruent to b mod m, then a to the m to the k power is congruent to b to the m to the k mod m to the k plus 1. Well, this looks like a clear induction proof. And I think for the induction proof, I would even start it at k equaling 0. So proof by induction. Yeah, we could have just said k equals 0, because when k is 0, this is, in fact, the hypothesis right here. For k equals 0, the statement is trivial. Trivially true. Okay, so let's suppose it's true for a given k. And consider k plus 1. Okay, so to be true for a given k means star right here is holding true. So what does star mean? That means a m to the k equals b m to the k plus some multiple of m to the k plus 1. So what do we want to call that multiple? L times m to the k plus 1, say. For some integer L. And now we're trying to prove this statement is true for k plus 1. So I want to raise both sides to the k plus 1 power. Well, I want to get a k plus 1 on the m, so I just raise both sides to the mth power, right? Let's see what that does. Because then I would have m to the k times m would give me an m to the k plus 1 here. And on the right-hand side, I'll just do a binomial expansion. And that should be good enough to get you going. Problem 8. Prove there are infinitely many primes of the form 4n minus 1. So this is going to be very similar to our classical proof that there's infinitely many primes, period. But here we're making a restriction that all of these primes are congruent to negative 1 mod 4. Okay, so proof by contradiction, as you would expect. Suppose there are finitely many such primes P1, P2 through Pk. Okay, so all of these primes are of the form 4n minus 1. So all the pi's are congruent to negative 1 mod 4. Prove there are infinitely many primes of this form. Okay. So how do we get a contradiction? So we need to come up with some big positive integer that will not be divisible by any one of these primes right here, and yet we know that it should be divisible by some prime that's congruent to negative 1 mod 4. Well, if we take the product of these numbers right here and I add 1, like we did in the standard method, would I be able to say that it's divisible by some prime congruent to -1 mod 4? So that's the problem. If we add 1, I can say it's got to be divisible by some prime other than these, but I can't tell you what its value is mod 4. So I have to do a little bit more than that. I want to come up with an integer that's congruent to -1 mod 4. So to write down a number that's congruent to -1 mod 4, I'll put a 4 here and subtract 1. Okay, so that's the strategy. Just write down a big number congruent to -1 mod 4. And let's call that n, capital N. So the question is, why is n divisible by some prime, some prime p congruent to -1 mod 4? That itself is a proof by contradiction. You say, well, suppose n, capital N, had no prime factors of this form, so it would be a product of primes that are congruent to 1 mod 4. Notice this is an odd number, so you don't need to worry about 2 being involved here. And if n was a product of primes that are congruent to 1 mod 4, what would the value of n be mod 4? So think about that. And then, so after you get n is divisible by some prime congruent to -1 mod 4, you say, could it be divisible by any of the pi's that we started with? And that's going to give you your contradiction. Problem 9. Prove that if f of x is a non-constant polynomial with integer coefficients, then f of x cannot represent a prime for every integer x. So again, proof by contradiction. Let's suppose it does represent a prime. For all integers. Well, then in particular f of 0 is a prime. Some prime p. And what would f of p? What could you tell me about f of p then? Well, p is congruent to 0 mod p. So f of p is congruent to f of 0, which is congruent to 0 mod p. So f of p is congruent to 0 mod p means that f of p is a multiple of p. And yet f of p is supposed to be a prime. Well, if f of p is a prime and it's divisible by p, what prime is it? And then think about f of 2p. Or more generally, f of k times p equals what? For any integer k. Well, think about this being a polynomial now. F of x is a non-constant polynomial, and it's equaling this what value for any k element of z. So graph the function. Here's your what value, and here's p, 2p, 3p, boom, boom, boom. So you're graphing a function, polynomial, and somehow it's just wobbling around and it keeps hitting this what value here. And ask, how is that possible? For a polynomial. Something's funny about this polynomial. Polynomial of degree n is supposed to do what? Okay? Think about how many zeros it can have. Think about what happens as it goes off, x goes off to infinity. Any number of things you can think about here to get a contradiction. Problem 10. Determine all integers k such that 10 to the k minus 1 is the sum of two squares of integers. So just start by exploring. Let's explore. Obviously, we want to start with k being 0. We won't have any fractions involved here. So when k is 0, 10 to the 0 minus 1. And then when k is 1, is that a sum of two squares? K equals 2 is when you first have to start thinking a little bit. There's a question, does this equal a squared plus b squared? And you can think about that one, whether you think you can succeed there or not. 64 plus 35, etc., etc. You can explore that. Okay. And now we want to think of some strategy. And a common strategy here is to do modular arithmetic when you're exploring questions of this type. So if 10 to the k minus 1 equals a squared plus b squared for some integers a and b, well, that would imply in particular that 10 to the k minus 1 is congruent to a squared plus b squared mod m for any value of m. And you might try mod 2, mod 3, mod 4, etc., until you find a modulus that you make progress with here. So if we tried mod 4, for instance, how is this possible? So what value is every square mod 4? So a squared mod 4. Well, we have 1 squared, 2 squared, 3 squared, and 4 squared. This is 1, 0, 1, 0. Mod 4. So the only squares you have mod 4 are 1 and 0. And then you ask, well, what values can we get if we added 2 squares? And that's the right-hand side. Now look at the left-hand side. What does this equal mod 4? Okay, and play with it like that. Problem 11. Prove that for any positive integer n, the sum of the reciprocals of the first n positive integers is not a whole number. And n has to be at least 2 here, of course. So Let's just add up that partial sum of the harmonic series here. So how do you add a bunch of fractions? Well, you've got to get a common denominator. So let's let L be the least common multiple of all the integers from 1 to n. Okay, that will be the least common denominator. So how do we put this into a fraction form? So you'll have 1 plus 1/2. Let's just write it out. And we'll write out a few terms here. So when I produce the common denominator, I'd have to multiply by L over L for the first one. This already has the 2. So I'd multiply by L over 2 times L over 2 on that one. And this already has a 3. So you'd have something like this. So you get L plus L over 2 plus L over 3 up on top. These look like fractions, but they're whole numbers up on the top. And then there's this big common denominator L right here. And the hint, well, we're trying to prove that this is not an integer. So here's a little lemma you'll want to think about. Show that if you have a fraction where the numerator is odd and the denominator is even, that this is never a whole number. And I claim that what we're looking at here is of this form, that this is an odd over an even. Okay, so you want to think about why is this true, that an odd over an even is never a natural number. And then the second thing you need to think about is why is the top? Why is the numerator odd? So think about what happens. You're multiplying top and bottom by something, and most of these numbers are going to be even. So I claim that exactly one of these numbers is odd. Because what would it take for that number up here to be odd? That means you would have divided out the biggest power of 2 sitting in this least common multiple. And the thing that you want to note is that if 2 to the k is the biggest power of 2 sitting less than or equal to n, then in fact that is the multiplicity of 2 in this least common multiple. So then 2 to the k is the power of 2 dividing L. And that should tell you why this top comes out to be an odd number. And we are done.